Hello and good afternoon, everybody. I hope you can hear me well and see me well as well. My name is Jiří Hartmann, and I would like to welcome you to this breakout session dedicated to digitally enabled modular cells for parts production. I'm located in ABB's Global Solution Center, located in the Czech Republic, and our core focus of activities is development and delivery of standard arc welding, laser welding, spot welding, and laser cutting production cells, and also turnkey systems to our customers. I have been working with ABB Robotics since almost 7 years now, and it's kind of funny situation because if I consider it, it's basically representing only one period of time, which represents one generation of successful car model. Despite this short period of time, I have seen a huge trend in the shift of production needs, basically coming from dedicated systems to flexible production lines. And basically, just a couple of years ago, we were only talking about dedicated lines which are capable to produce large series of parts, where there was no parts variability or very limited parts variability in terms of left and right variant of such specific part. And the main KPI of such line was basically the performance in terms of cycle time, so produce as fast as possible. Then the trend came to introduce more product variants into the production system, so the same equipment is capable to produce really different parts. The other KPI which appeared was the quality, because production of scrap is expensive and also difficult to handle. Another element which appeared was production traceability, so that we can really track what was produced when and how. These kind of systems are more or less modular in the sense that they are capable to accommodate production of different parts. And the next step is right now popping up, which is the demand to have a scalable production system which can meet the request in terms of production volumes. Basically, to avoid investment in the full capacity from day one of the production, and also on the same time at the end of life of the production system to be able to shrink the production capacity with declining production demands. The main KPI is OEE, which is in fact combining all the other components from the previous steps, like performance, quality, and availability at the same time. So basically, this kind of full automation ecosystem is created. And what is typical for such production system is that it's consisted of production cells. So coming from a ground-mounted single-purpose line to cell-based production system. And how to assure that? Basically, the short answer to assure such job is digitalization and collecting of the information from the production system. We start with robot, because robot is the key element of each and every our system which is delivered to the customer. And basically from the robot we can collect many interesting information which are further used for some actions. Basically from the robot itself we collect mainly maintenance data, so that we know when the robot should be serviced and how what should be serviced in particular moment. Also, the robot as such is just a product, but somehow it is programmed. And collecting the data from the robot, we can also propose some movement optimization, so that we avoid some unnecessary movements or some hard movements which are affecting the lifetime of the robot in its entire lifetime. And if we have more robots, we can get some statistical or analytical data at the end of the day, so that we can, from a lot of data sets which we get from the robots, we can really determine that something is going wrong in some particular robot unit. And basically, we can predict failures before they happen. So, for instance, if there is one failing gearbox which is still working and it is not visible, in the production, we can already get it from the data we get. And basically, we can plan to exchange the gearbox during some standard maintenance periods. So basically, we prevent malfunctions in our systems. With this data, we are addressing the performance. In other words, to keep the robot alive under any circumstances. Once we connect to the robot some auxiliary equipment, in this specific case, it's a welding power source, we can get much more from the system. We can get weld data management, and we can go to seam level tracking. During the production, we can propose and perform some optimizations on welding quality. And if we have multiple systems, we can also propose some fleet management, because typically in large robot production systems, we have many robots, and some of them are performing more, some of them are performing not so many operations. So maybe we can even balance production operations in the complete fleet, so that we can have balanced wear use, and also we can have balanced maintenance schedules for each and every unit. And if we wrap everything together with the safety fencing and other equipment, we are already speaking about the production cell. In this specific case, it's a welding cell, ABB Flex Arc. It's a standard product, and basically this is a smallest comprehensive element which can be incorporated into the production system, because from this smallest unit, a cell, we can collect all the data which are somehow affecting the production. So we have full data collection from the cell. We can introduce the production traceability. We can propose cycle time optimization, not only on the level of welding process or movement of the robot, but also taking into the consideration, for instance, the loading of the input components and unloading of finished part. With that, we can also proceed further with complete OEE analysis, and we are speaking about the possibility to integrate the cell into the complete factory ecosystem. Once we start thinking about creating a complete complex production system, which is consisted from multiple cells, it's worth to stop a bit and talk about the loading concepts, because we have, I would say, three basic types: how to feed the machine, how to tend the machine. And the most easy concept is to leave everything on operators, because we are completely excluding the logistics of input components and finished parts. And it's for us very easy to integrate such kind of cell in the production system. On the other hand, we need to develop a Pokayoke concept, so that we are assuring that the cell really receives those parts which are planned, that are being produced, and there are no collisions with wrong parts and so on. And we are completely dependent on operators, which is the biggest bottleneck actually in this concept, because operators are very different when it comes to the new operator, which is just starting his activities or her activities with the machine, or a skilled operator. Actually, one customer just recently even requested us to consider during our calculations of the cycle time also the tiredness of the operator during the shift, because we can propose a functional system which is somehow capable to meet the cycle time requirement of the customer, but it can be very difficult for the operator to catch up. So we need to really estimate also what is in hands of the operator to be able to really have an efficient production system. So as such kind of cell concept, it's typically great for a single component or single cell production system, or some smaller systems. But on the other hand, sometimes we are also delivering even larger systems. This particular line was consisting of 15 flex arc cells next to each other, and basically the line is up and running, but it's completely dependent on the operators. Another bottleneck is that operator is the one who decides which part is okay and which part is not okay, and how to treat this part later. It can generate errors or failures, because when the operator decides to release the part to the next production step, we can create really a scrap or not okay parts at the end of the day. Another disadvantage is that we need to place these cells very close to each other to avoid operators walking long distances. Another opportunity or possibility is to utilize handling robots. Two ways are possible. The one you can see on the picture right now, it's the cell which is designed to be loaded by the operator. So small components are still loaded by the operator, but the handling robot unloads a finished part. Basically, there are two advantages in that. First of all, the handling robot helps the operator not to carry heavy loads because finished part can be particularly quite heavy. And the second very important step is that it's the machine which can decide what to do with OK and not OK part. So if OK part is produced, handling robot releases the part as green to the output conveyor, and if the part is somehow suspicious or even marked as not OK, robot either brings the part to the trash or it can bring the part to some check, inspection, or a rework space inside the unloading area of the cell, and then it's up to the operator or some other staff to decide what to do with the part or how to rework it. It has a huge benefit, especially when we consider the cell which is not only unloaded by handling robot but also loaded by the robot. So input components are really loaded by handling robots, and with that we can create really complex systems, large ones, even though they are cell-based. Here on the screen you can see that we have a line which is consisting of several manufacturing cells, and they are fed by handling robots placed on the track motions. Basically, such line can be very complex, and the drawback which we see, I think it's quite clear, because the footprint of that production system is very dense. There are many other processes around, and if we later on decide to modify something or add something or remove something, we are basically speaking about production stop and modification of the complete line. The next step, which is the most flexible one, is to utilize AGVs. This is the most trendy segment at the moment. And basically, AGV solves everything, because we can have a standard cell which can also accommodate the needs to load or to do some specific tasks by the operator, like the one which you can see on the picture. Or we can have really independent cell which allows AGV to go inside the welding area, and then AGV can really behave as a carriage, including fixture of the complete part, and the part is welded directly on the AGV. This specific type, basically, it's not very well visible here, but on the side of the cell, there is also a handling robot, which is basically reaching the AGV, bringing parts to the production cell. Then the cell can wait for some small components to be added by the operator, and then after the product is welded and finished, the handling robot gives the part back to the AGV, and then AGV proceeds with the part for further operations. With that, we are already speaking about a complete full logistics automation, and it's a base milestone to really get some flexible production system in the production area. Complex production system is unfortunately not about only our ABB production cells. Sometimes we need to incorporate some other machines as well. And therefore, we have also created another product which we called Flex Loader. And basically, Flex Loader is a machine which is taking care about the feeding of several machines. It can be really a lot of variants and different types of machines which are really needed for the production, like the CNC machine, it could be sandblasting machine, leakage test machine, and so on and so on. So there are numerous machines which can be fed by a flex loader system. Flex loader system basically consists from the main body, which is in the middle, and in the back side of that cell there is a robot. It can be different type of robots installed depending on the machine, depending on the requested payload of the robot, and of course it needs to be in the close surrounding area to the machine, which is stand by the robot, so that we can reach the machine itself. And then there is a loading area which can really differ from case to case. The flex loader system, it's not one product, it's a complete family of the products which basically differ by the loading concept. So we can have a tray system, conveyor system, or a random feed system with a bin picking software. So we have optical camera inside the flex loader system to really detect parts which we need to bring, their position, and so on. Then we can have bin system, and I would say the most important for me in this case is the AGV system. So basically, this kind of cell is able to incorporate the same AGV which is coming from a production cell like the one before, the welding cell, and it can supply parts for further processing and then take these parts to another steps. So basically, flex loader is a key element for us to integrate such machines into the complex production systems. The picture you are looking at the moment, it's a so-called kitting zone. And kitting zone, it's I would say, some kind of central station for a complex modular system, because kitting zone basically solves the issue with input parts, with input components which are entering the production process. And if you take a look deeply, you can basically see a set of flex loaders which are feeding the machines. And the machine in this specific case is the AGV. So basically AGV here in the train station receives all parts which are necessary to be processed later on. And also the flex load system can provide some easy tasks, easy operations straight on in the kitting zone. Like here on the left side, two first machines, they are already equipped with a nut welding machine. So the first operations are actually happening already here. And then these parts are taking to further operations, such as welding and other operations as well. So to summarize it, how to really build such a system? I would say our individual cells, they are prepared for your digital transformation already, because they are digitally enabled. We collect all the data from our own equipment, but also from third-party equipment. So we have our own proprietary protocol for communication, but we accept, or we are open to other IoT standards like OpenUA or MQTT and also the others. So we are collecting all the necessary data, and each cell as an individual unit already out of the box provides some visualization of some specific items. So we are having production screens in each and every cell, or you can connect to it from your web browser, and you can really track, for instance, OEE, cycle time, and so on each specific machine. Then we are able to publish these data to the outer world. So if there is any higher level control system or some cloud-based system, we are able to export these data and send these data from individual cells to such system to have a comprehensive overview about everything. And then once we have such kind of system, we can provide some business applications. For instance, really cycle time analysis. So it's not just an overview about the cycle time, but we can provide really deep dive into any specific item which can influence the cycle time, which is not only, I don't know, the power source. It's not just the robot. It can be operator, it can be feeding machine, it can be even temperature, and so on and so on. And this can be analyzed in such application. So here I would like to show you some practical usage of digitalization, which we already do right now. And basically one of them is so-called virtual commissioning. And basically virtual commissioning means that we are able to design, build, test, and run a production system. It can be cell, but it can be a complete production line virtually before we make it physically. And the reason or the nature behind is that we are able to run the virtual commissioning and solve specific issues before we make them in the real world, which is later on very difficult, sometimes difficult, costly, sometimes it can be even impossible to solve later on. For that, I have a short video for you. You can see it now, or I hope you can see it now. Basically, we have a virtual cell, which is created in our robot studio, our programming software. And here we are basically demonstrating the communication of such virtual system with a real PLC, which you can see right now. The screen on the right, it's a CIMIT, and basically this is the interface which provides the communication between the real PLC and the virtual system. So we can do the virtual commissioning. We have fixtures already installed. We have done already the programming in the Robot Studio program, and also the logic of the PLC is done. So we can really do the commissioning as such on the virtual machine to see that everything is running. Yeah. Of course, still it's the simulation, but we are really sending real signals and receiving real signals from the virtual machine, so we can check that everything is running according to our expectations. Here you see individual signals so that we can really check that clamps are working and sequences are working according the program was made. Okay, great. Coming back to the presentation. Exactly the opposite, basically, of virtual commissioning is a digital twin. When we are talking about digital twin, we already have a real system out there and running, producing, and we are discussing with our customers some introduction of new products, production optimization, and so on. It's good to do that virtually before we apply that physically, because we can solve a lot of issues and we can introduce new parts without any intervention on the real system or long intervention on the real system. For that, I have also a short video which we called virtual training. Basically, here we can provide a simulation also in our Robot Studio system for the employees of our customers to be able to train them. So we use the 3D goggles and 3D system to ensure that the operator is able to see everything like in real life. And we can, because we have basically virtual real machine which is behaving exactly the same like the one which we have on the shop floor, we can train the operator. We can show him look and feel like the real world, and he can already learn how to operate the machine or maintain the machine in the virtual world without any risk and without any stoppage in the production. As well, the complete program of the real system is loaded in the virtual system. So basically we can we can adapt it, we can go through it, we can see it on the flex pendant unit, and yeah, everything is exactly the same like the virtual, like the real machine. Okay, and coming back to the presentation, I have one last slide, and basically it's something about augmented reality that we use a 3D camera as well to scan or to make a 3D copy, a 3D picture of the real system, which we later on import into the robot studio as well. And with that, we are working with our customers specifically on requests when they want to change, for instance, the robot. So they have an old robot type and they would like to exchange it for a larger one, for instance. And we need to be sure before we apply that robot to the system, we need to be sure that robot can move freely without any obstacles, without any collisions, and we need to assure that the reachability is okay for the robot. So the easiest way for us to do that without really influencing the real production is to make a 3D copy of that and play with that in the virtual world. So what happened here on the picture, we loaded a 3D photo of the machine and we loaded virtual robot on that. So we check everything in the robot studio virtually. Again, we can use these 3D goggles like on the video before. We can walk in and really observe how the robot behaves, what is doing, if there is no conflict, and so on. And if everything is safe and feasible, we can proceed with robot removal and robot exchange in the real world. That's it, guys. Thanks a lot for your attention. Thanks for your time you devoted to this breakout session. I have one last thing to do. I would like to ask you if you would like to spend and give us slight feedback to this breakout session. Please use your mobile phone and aim your camera to the QR code, which will bring you to the feedback page. And if there are any questions, please don't hesitate to use chat. I will remain available for you here for a couple of minutes before we end this session. Thanks a lot for your attention. Okay, no questions are popping up, so one last minute. Okay, nothing here. So thanks a lot once again for your attention, and I wish you a nice day. Bye bye.